You know, I went to a conference last week, arranged by the Swedish Energy Agency. And there I learned something that struck me. Sweden today has actually more installed wind power than Denmark. Did you hear that? You know, that's far away from my reality. My reality was that Denmark was the country with the wind power. But today, Sweden has more. So it's been an enormous growth in wind power in Sweden. And that's in general so in northern countries. Of course, we have special conditions in Sweden. And that is, of course, the cold weather. The cold air is, of course, an advantage if you want to draw energy from it, because it's heavier. The cold air is more dense than warm air, so that means you can harvest a lot more energy from it with the same amount of wind. But we also have a lot of wind in Sweden. We have mountains and we have coastlines where it's quite windy all the year round. But now to my project here and why I am here. And that is we get sometimes ice on wind turbines. And that ice, it's a problem. It will stuck on the blades on the wind turbine, and it will decrease the efficiency of the turbine first of all. And if it's severe enough, it can actually force the wind turbine to a complete stop. And today we have a problem is that we can actually not. We have difficulty to predict when it shall actually happens. And that is because it's a combination of several meteorological parameters, not only the temperature and the wind speed, but also the amount of liquid water that is in the air and is supercooled, and also the size of these water droplets. So the fog that you see contains, of course, small water droplets, but they are different in size. And sometimes, if they are big enough, they will stuck to the surface and freeze. So, the normal parameters that we have, temperature, wind speed, that's quite common that we measure and we can predict it. But also, the size and the amount of liquid water is decisive for the amount of ice that we actually gain. So what's the possibilities of measuring that? Well, we have today models for short-term prediction of ice load. But, and we also have de-icing equipment on the wind turbines. But to know when or where it is actually formed, we need a local measurement of the icing parameters, so that these operators can receive an early warning of when it should actually happen. So, and also the forecasts and the models that we use for prediction can be, of course, be improved with this feedback. So how do we know when the ice is actually formed? Yes, we have some direct methods. And one was the one that Benny and Patrick was talking about previously. It's actually watch the ice, see when it grows. We can also measure it by, for example, measuring the effect curve of the generator. Or we can also calculate this the ice that we expect by measuring the environmental conditions. So our indirect measuring method that we have using, and that is through shadow graph imaging. That's actually to take pictures of the water droplets. By that we can actually both measure the size and the concentration. And this instrument that we are measuring with, it should ideally then measure as close to the highest point of the wind turbine as possible. And the instrument should be durable, of course, and cost efficient and suitable for remote operation. And we don't have that kind of instrument today. Yeah, we have used, of course, the recent technical development. For example, digital image sensors. You know, in every camera you have, there is in every mobile, I would say, there is a camera, and the development of these CMOS cameras has exploded. They've become better and cheaper, so that makes that way possible to have a good camera. And we also have a development in powerful light sources like the blue LED that's enabling lighting. The limitations we have actually are in the properties of the illuminating light. That means, then I talk about the wavelength of the light, that is. And we also talk about the resolution of the sensor and the optics. Possibility we have by measuring, and if we have a measuring of each particle by particle measuring, then we can analyze the microstructure of the cloud as well. This is a sketch of the equipment that we have used. It's a little bit, if I go here, you see a camera and we put a lens on it, and we have a illuminator here. So they are facing each other. So we point the LED directly into the camera, so we get a very good exposure. And if the pulse is short enough from that exposure, then we will get a shadow image of the smallest particle. Yeah, here are some results. It's hard to see here, but it's droplets anyway. It's examples of droplets. And we detect them. We detect some of these. You see some of them are out of focus and some are in focus. But by calculating the ones that are in focus, we can see that, okay, we get a liquid water content. We have 16 grams per cubic meter, and we have a medium volume of 38. Here's another example, quick example, and then I will stop, of smaller droplets. So it's a completely different scenario, but we can still find them in this structure. We have some that are in focus, and most are not in focus. And then we calculate a new picture. So if we have that information, we can actually say that, okay, in this case it wouldn't have been ice, maybe, if the wind, but in this case it would have been ice. So there you go. So I will run through this very quickly. This is the prototype that we have built and we are going to test during this autumn and winter. It consists, I've built in all the previous, the camera and the lighting in one box each, and then we have a stream of air that passes through and that we analyze. And now we have also an environment in which we can simulate the the reality a little bit. We will also purchase a reference instrument. These are existing instruments that are built on a completely different technology, but they are also much more advanced and more expensive. So they are not a little bit different. So, oh, that was the last slide. So thank you very much.